Yes, sir. Recording started.
Right. So, welcome everyone to this course on high performance computing under NSM. And I see from the participant list that there are multiple of you who have done courses earlier as well. So, thank you for your enthusiasm and welcome. Special welcome to the people who are attending an NSM course for the first time. This particular course is divided into multiple modules, as our instructors will be telling, and the course is going to be delivered by four of our colleagues, Dr. Praveen Alapati, Brahmaya Gandham, Dr. Saurabh Kaikar, and Dr. Kalyan TV. I'm going to introduce each one of them. Dr. Praveen Alapati is assistant professor at Equal Central School of Engineering, Mahindra University. He holds PhD from IIT Madras, and his research interests are the design of concurrent data structures and high performance computing. He has a good number of publications in reputed journals and conferences, and he is also a member of IEEE and ACM. Brahmaya Gandham, whom you have probably encountered in an earlier NSM course in a different role, he is a PhD scholar working with Dr. Praveen. His research area is high performance computing, and his current work focuses on the development of locking mechanisms and concurrent data structures. He is also a member of the ACM. Dr. Saurabh Kaikar is a research scientist in Parallel Computing Lab at Intel. He completed PhD also from IIT Madras, and his research interests lie in parallel and distributed computing, compilers, architecture-aware optimizations. His PhD thesis focused on locking protocols for parallel accesses to the in-memory hierarchical data structures. He is a recipient of the Institute Research Award at IIT Madras in 2019, Distinguished Paper Award at PPOP 2016, and winner of Intel's Parallel Coding Challenge at HPC 2016. Our fourth speaker is who is going to start this session is Dr. Venkata Kalyan. He is an assistant professor in the Department of Computer Science at IIT Roper. Prior to this, he was a hardware performance architect in the Power Systems Performance team, part of India Systems Development Lab at IBM India. His research interests lie in the memory hierarchy exploration, alternate computing techniques, and low power energy efficient designs. He has several publications and patents to his name. Dr. Kalyan received his PhD at IIT Madras. He is also a member of IEEE and ACM. So without further ado, I am going to hand it over to the speakers who are also, because some of you do have these questions as to whether I should attend the first session or the second session, how they are distributed, etc. So I think all of this is going to get covered. So I hand it over to the instructors.
I hope I'm audible. Thank you, Rupesh, for the kind introduction of all the the instructors of this course. So I'll quickly walk through the flow of the course. So overall, there will be 12 sessions. Each session is 2 hours long, and there is a break of 15 minutes after the first session, right? And we will have the question and answers preferably at the end of the session, or the way the speakers would suggest, right, based on the topic, etc. So a quick walkthrough of the course contents. We are going to start with some very basic topics today, and which will be handled by Dr. Praveen and myself. And following that, on 2nd of November, we will have a 2-hour session on OpenMP by Dr. Saurabh. And he's going to continue discussion on MPI on 7th of November, along with Dr. Praveen. Following that, we will have synchronization basics by Dr. Praveen on 9th, and on 14th, Mr. Brahmaya will be discussing about spin locks, followed by Q locks on 16th of November, right? And again, we'll have one more session by Dr. Saurabh on concurrent data structures. starting with trees, and then followed by concurrent hashing by myself, right? And then on 28th, I'm going to discuss on some basic metrics based on which we evaluate and measure the performance. And the last 3 sessions on 30th November, 5th and 7th December will be primarily focused on GPUs handled by Dr. Praveen. So as you can see, we slowly move from typical CPU-based implementations issues to GPUs. And this course is going to touch upon many of the fundamental topics mentioned here. So other speakers, do you want to add anything here? Okay.
This plan sounds good.
Good. Continue,
Okay.
Kalyan.
Fine. And just a small caveat here, maybe the content might go a little here or there within the session. So, but overall, we are going to stick with this flow, right? Okay. So let me kick off the discussions. I'm going to present something very popularly known graph, right? So here over the past 4 or 5 decades, how things have progressed on the CPU front, starting from mid 1960s to 2020, right? So here we see different trends, right? So the very first one here, I hope you can see my pointer, right? The very top one is the number of transistors that are getting integrated year after year. There has been tremendous scaling that has been observed, right? And following the availability of multiple transistors, etc. So we have used those transistors for building much more complex and bigger or multiple of such logics to speed up our operations, right? Along with the number of transistors getting increased over the years on a single chip, we also see that because the transistors are getting smaller and smaller, the frequency of operation is also scaling, right? Of course, there is a small break in this trend somewhere in mid 2000s. We are going to come to that after a few slides, right? And so none of this comes freely. So as the number of transistors or the logic that is getting integrated onto the chip is increasing, so does the power, right? So the fourth line here, the red one, is the power that we are burning over the across different chips, right? It has been increasing steadily, and again post mid 2000 there has been a small break, and then the blue graph is the single threaded performance. So we have been getting improvement in single threaded performance over the years. Of course, it is getting a little saturated of late, but still whatever needs to be extracted is being done, right? And the last graph or the last trend is the number of logical cores that are on a single chip, right? And till mid 2000 there has been only one core per chip, and after that we see a trend for multiple cores on the chip, right? Like I said, it's a very popular graph studied numerous times to understand how things have progressed. We are going to look at these a little more closely to understand how that has impacted the program development also, right? So, and on the other end, we have the GPUs, how the GPUs have evolved over the years, right? On the y-axis, you see the G-flops. And we are looking at the single precision floating point performance only, right? So over the years, yes, there has been just one second, I see some issue here. Okay, or perhaps here. Yeah. So over the years, we have been seeing quite a bit of improvement on the GPUs, right? Currently, we are the most popular is the A100, right? So over the years, there is an increase in the trend, but the other concerning factor is the power that the GPU is burning, right? On the secondary y-axis, that's what we see. So, on the color grading, that's what we see. We are currently burning a lot, which is indicated by thermal design power index, TDP. Whenever you buy a processor, either it's CPU or GPU, it's going to come with a TDP rating, and this is important because you need to augment the processor with sufficient cooling. Otherwise, the chip is going to burn out, right? Literally. So yes, GPU's performance has been increasing. Power is an issue, right? The CPUs have been seeing an upward trend of performance improvement. So let's try to go a little more in detail on how we have achieved this. So the road to performance started off with a very, very basic observation, right? Which is how we measure the performance, right? In the very basic terms, it is said to be execution time of a program, right? It is given as a product of the total instructions that have been executed times how many cycles we are taking to execute one instruction. So we call it CPI, cycles per instruction. This is an average number. So a few instructions take more cycles, few instructions takes less cycles, and followed by the speed of operation. So here it is given as cycle time, which is 1 upon frequency, right? So the very first thought the designers, CPU designers had was let's move from single cycle design to a multi-cycle design, meaning so if we are to execute one single instruction, so they have logically divided this into steps of fetch, decode, execute, access the memory if required, and followed by updating the registers, destination registers, right? Now, in both single cycle and multi-cycle design, we go through all these stages. Here I've taken example of only 5, right? Now, in the single cycle design, we wait, or the cycle time is the time taken by all these 5 stages together. But in multi-cycle design, we finish one stage in one cycle. So in a way, if you say that for single cycle design, X is the time, and for all for simplicity, let's assume it takes still overall the same time in multi-cycle design, but the frequency of operation is slightly faster. So here, if the cycle time is Y, if we assume that all the tasks are equal, then we are actually running 5 times faster. But does it actually reflect in performance improvement of the program? So there is a catch here, which is the CPI. Here, the cycles per instruction for the single cycle design, as the name says, is 1, right? And the cycle time that we consider is X. But on the multi-cycle front, the cycles per instruction is 5 now. 5 cycles of Y cycle time each, right? And so we can say that, okay, single cycle design is running at low frequency, multi-cycle design is running at high frequency, right? But are they taking, is the multi-cycle design faster? No, because the execution time is now same. So the instruction count or the program that we are running is same. So the instruction count remains same, and the product CPI times the cycle time is same, both in the single cycle design and multi-cycle design. Now, if we are wondering why this effort has been made to move from single cycle to multi-cycle, it is a baby step that the designers took before they made the leap to what's called pipelining. Okay, because this in order to answer how we can improve further, right? From a non-pipelined or unpipelined processor, we have moved to pipeline processor, right? So a very high-level overview of what the unpipelined or non-pipelined processor would look like. In the non-pipelined version, we pick one instruction. We basically we fetch it, decode it, execute it. If there is a memory access, we do it, and then we update the destination registers. Only when this particular instructions write back or register update state completes, then we pick the second instruction following third instruction. So we go one after another, right? So the CPI is 5, and to execute 3 instructions, we are going to take 15 cycles. Now, what is the pipeline version, right? So we take the first the instruction, we fetch it. In the very next cycle, so if we assume that the one column is per one cycle, in the very first cycle, we are going to fetch instruction 1. In second cycle, the instruction 1 will be moved to the decode stage and instruction 2 will be fetched. We are not going to make the fetch stage to be idle. So we want to engage it, right? So in the third cycle, right, I1 moves to the execute stage, I2 moves to the decode, and I3 moves to the fetch. So on and so forth. In the steady state, if you try to visualize, one instruction will be in the write back, another will be the next instruction will be in the memory, the instruction which comes later, right after that, will be in the execute, so on and so forth. So we are able to engage all the different stages of the hardware, right, involved in the instruction execution to get better performance. Is that so? So let's notice that. So instruction 1 completes in the 5th cycle, instruction 2 completes in the 6th, instruction 3 completes by 7th cycle. So in the unpipelined processor, we were taking 15 cycles, but in the pipeline processor, we are actually taking 7 cycles. In steady state, what we can potentially see is we will be completing or executing one instruction every cycle. So that's the best case. Of course, there are a lot of practical implementations, as you are aware, what's called hazards. There can be structural hazards, data hazards, and control hazards, right? These are primarily coming because of the dependencies between the instructions. Of course, structural hazard is more primarily because of hardware. If you put that point aside, both the data and control are primarily because of the data dependency. See, when we write a program if we bring in some data or if we compute some data, we want it to be used later on. That's the reason we are computing the data, meaning that there will be a consumer instruction somewhere down the lane, and this instruction is producing the result. It can be a simple load store instruction or an ALU instruction, right? Now, this is the data hazard. Whenever there is a data hazard, then the pipeline will have what's called bubbles, right? Bubble effectively means that we are not able to engage that particular pipeline stage, or it's idle in that pipeline stage, right? And if we look at the control hazards, right, the typical if-else, the basic one, wherever there is a condition check, if-else, switch, or anything, even in your loops, right? Wherever there is a condition check, we don't know what would be the next instruction. Either we are going to continue with the next instruction, or if, let's say, in a simple if and else, we don't know whether we are going to execute the if part or else part until we are going to resolve that condition, right? Which happens only in the execute stage. So we if we don't address this problem, right, there will be again a lot more bubbles in the pipeline. So over the years, the CPU designers, though they started with the simple pipeline notion, whatever we presented here is a very theoretical version, right? They started addressing each of these hazards effectively, right, by data forwarding or let's say branch prediction, etc., to reduce these bubbles. Now, bubbles are bad for performance. Okay, so ideal case is that if we have end stage pipeline, then when compared to a non-pipeline version, we will get an performance speed up, or the speed up of n times. So that is the ideal. So that's where things have progressed. So we have used the additional transistors that were provided to us across the generations, right, for enabling much complex hardware to address these hazards. Now, the question remains, can we do any better? So we did n times improvement. Let's go with the ideal case, but can we do any better? That's where things have been explored further. Why should I fetch or decode only one instruction in one cycle? So can I fetch more than one? So that's if I am able to do that, it's called pipeline. Width of the pipeline has been increased. Now, whatever pipeline we saw, a single row of 5 stages. Imagine that has been replicated in the second dimension, meaning that let's say if we have 4 instances of it, I can effectively fetch 4 instructions, decode 4 instructions, execute 4 instructions, and eventually retire or complete 4 instructions in one cycle. Right. So this was one major breakthrough, and accordingly, a very, very high performing complex pipeline was developed, which we call superscalar pipelines. Right. So what we have discussed in the previous slide was primarily a simple scalar pipeline. Right. Of course, here there is one added extension that comes as an answer to how much more we can reduce the stalls or bubbles in the pipeline. Now we are fetching more instructions, or we are working with more instructions in parallel, meaning that we will end up with more situations where these data and control hazards might be potentially there, right? So that's when the designers started asking, why should I execute the program in order? In order meaning that if your program has, let's say, 100 instructions, let's label them 1, 2, 3, 4 till 100. Should I execute instruction 10 only after the first 9 have been executed, or can I go ahead and execute instruction 10 before if I see any issue with any of the earlier instructions? So that's what we call as out of order processing, out of order execution. So there, because we are fetching and decoding multiple instructions, basically we are aware of the status of multiple instructions in any cycle. We will go ahead and issue it to the execute stage or the execution units, whichever is having no dependency, either the data or control, right? So now if we are able to do execute the instructions out of order, we need to take extra care to retire or complete the instructions in order. So at the fag end of the pipeline, we have some extra hardware. Typically, it would be a reorder buffer where the instructions get stacked up, and there we are going to commit in order. So we are going to fetch in order, but process them out of order and commit in order so that the correctness is still maintained. So in addition to the out of order execution, we have what's called dynamic scheduling. Okay. And speculation, meaning whenever there is a branch, or said earlier, whenever there was a control hazard, we don't know which set of instructions would be executed. So we go ahead with one assumption or study whatever we have noticed earlier, that the behavior of this particular branch is maybe it is always taken or always not taken. Accordingly, we go ahead and process, right? So all these are part of complex superscalar cores. Now, further, can we execute or can we process more than one program at the same time? So that was the question asked. And because we had a lot of transistors at our disposal, we said, okay, why not? We will do what's called multi-threading, right? So there are three variants to it: fine-grained multi-threading, coarse-grained multi-threading, and simultaneous multi-threading, SMT in short, where the smaller chunks of the program are run on the same hardware, primarily to keep it as busy as possible. Now, if some particular program has seen misprediction, then we have to flush the entire pipeline and restart it with the correct. That is a small penalty, but it becomes higher and higher as we go with more deeper pipelines. Currently, in almost all our desktop and even mobile process, we typically have 15, 16 pipelines to start with. Right now, whenever there is a misprediction, the penalty we pay is very high. And following that, we also have another potential issue with the memory, meaning that we are assuming that the data is readily available to us, but it might not be the case. So whenever we don't find the data near to us, so we spend long time to get it from our storage to the primary memory and eventually close it to the processor, right? So this is a long latency event. During that time, we don't want to keep the pipeline free. So what we do is we take another instance of the program of another small so chunk of work from the same program or different program and start working with it, right? So here is a illustration. I think, yeah. So the source I have given is very descriptive, and this too is a very well-known optimization at the hardware that people have come up with. So the superscalar processor. So okay, let me explain the figure once. So each column pertains to, let's say, one pipeline, right? For simplicity only, right? So it means that here we have 4 width pipeline. So we want to keep all these 4 slots busy every cycle. So that is the row. So one row corresponds to one cycle after another, etc., etc. So how do we interpret it? Is in here, in the very first cycle, we were able to engage out of the 4 slots, only 2 slots of the pipeline. In the second cycle, we were able to engage only 1 slot. In the third cycle, we were able to engage 2. In the fourth cycle, we were able to engage 3 slots. And in fifth and sixth, we were practically not doing anything. These, you can say, are the bubbles that we were talking earlier. So earlier we had only bubbles in one direction, but now we have bubbles on both row and column, right? So here we see that there are a lot of bubbles. So we extended this superscalar to support what's called multi-threading, where we have multiple threads available to us. And in fine-grained multi-threading, what we do is in each cycle, we pick one thread. So let's say we have 4 threads. Okay, we have 5 threads here in the illustration, thread 1, 2, 3, 4, 5, right? In the first cycle, we took instructions from the thread 1. We started working with it. And then in the second cycle, we picked instructions from thread 2, in the third cycle from thread 3, so on and so forth, right? We are shifting the thread ID after each cycle. In coarse-grained multi-threading, what happens is we pick one thread and we start executing the instructions from that. And only when there is a long latency event, we switch to another thread. Okay, so that is the reason we see that here for the first 4 cycles, we were working on thread 1, and then we picked thread 2, then the next 3 cycles, thread 3, and wherever there's a long latency event, meaning it can be an interrupt or it can be any memory request, right? So we make a switch. And in simultaneous multi-threading, we do there's something similar on the second dimension also, meaning in each cycle we are going to look at multiple threads and look for any instructions that can be potentially executed. So here let's try to understand this. Okay, are you able to see my pointer? Yeah. So in the very first cycle, we have 2 instructions picked from thread 1, 1 instruction from thread 2, and we have 1 bubble here. And then in the second cycle, we picked 1 instruction from thread 1, 1 instruction from thread 3, then 2 instructions from thread 4. So that's how this simultaneous multi-threading goes. Now, what is it that we are actually achieving here is we want to keep these pipeline stages as busy as possible. Okay, so and there is one other variant of it, which is multi-processing, where we pick we are practically dividing the core into, here in this example, 2 chunks, and we start working on the instructions of individual processes. Right here also you see that there is a possibility of a lot of bubbles. So this is not the perfect match, and SMT is found to be the most efficient in the sense that whatever hardware is there, it is able to keep it engaged as much as possible and and speed up multiple threads effectively. So if you look at one particular core here, right? So if it was a single core, if we consider a single core CPU with hyperthreading enabled, right? So it would have 2 register files, 1 for each of the threads, right? And also a few other status registers like the PC, etc. will be maintained, right? And but the important point to note it is that the ALU, which can have potentially multiple execution units, etc., is common, and so is the bus interface. Now, if this particular CPU was not supporting hyperthreading, then only the hardware in the red box would have been ideally there. And if you notice, even though we moved from no hyperthreading to supporting hyperthreading with, let's say, 2 threads here, the hardware actually did not double, but rather we are only adding additional components that help us to work with this hyperthreading, basically to keep the status information of both the threads. So excuse me. So this is with a single core. That's how things have evolved. Just a quick recap. We started with a single cycle execution model, and now we are at SMT level. But still, things were not as simple as they looked, because here there has been a change in the trend in mid 2000s, roughly in 2004-5 time. What people noticed is the power that the single CPU or single core is burning is going out of hands. Right, at that time there were a lot of memes, if you can call them, going around that we can actually use that heat to make something, cook something, etc. So as an answer to that, the CPU designers have come with the multi-cores design, meaning instead of having one complex core, we will use the same the available transistors to create multiple simple cores, right? So this was what's called power wall, right? Because we were not able to dissipate the power generated effectively, leading to burning of chips. So from the single core to multi-core chips, right, there has been an increasing trend. And now if you look at if you look at any of your typical desktop PCs or even workstations, you will have tens of cores. Even your mobile phone has 8 cores now, 8 cores and 12 cores in some of them, right? So again, the available hardware was efficiently used by the CPU designers, and till this point there was practically no impact on the programmers till the mid 2000s point, because they were happily enjoying the faster hardware, right? A faster hardware which with high compute capability. But what happened late after that is, instead of having one core, we have multi-core, and it's the task has been shifted to the programmers end to see how we can keep these multiple cores engaged, right? So that's when the parallel programming concept got a big boost. Earlier it was only looked at for predominantly scientific applications, but after multi-core process have evolved, every programmer started thinking about parallel processing. Now, how do we visualize the code to run on multiple parallel cores, right? So right now it is by default we start thinking about it. So that's where we are currently. And the GPUs also fueled this, because of course, Dr. Praveen is going to touch upon that. The way GPUs work, again, is that they have thousands of small cores or small processing units or SMs, there are different names, right? Which the programmer needs to engage. Yes, is there any question? Okay. Now, if you go back how things have progressed from superscalars to supporting out-of-order processing to supporting multi-threading, we extended it to have multi-core processors or multi-core architectures, right? This is only the compute part. There is the other part, which is memory, right? We are going to touch upon that soon. So from the way things have evolved from the single cycle to the multi-core architectures, basically we were trying to encache on different levels of parallelisms, right? So till the out of order processing, it is basically the instruction level parallelism. And then from multi-threading to multi-core architectures, we were trying to extract parallelism at the application level. So a few desktop process, I think this is now currently redundant. We have complex multi-core processors even in our small desktops. Intel and AMD have been leading. Of course, okay. There is a question. Okay, in layman terms, what is the difference between threads and cores? Before I answer that, let me give a clarity on the notion of threads. So there are software threads and hardware threads. So what I have been discussing is more on the hardware threads or hardware context, you can say, right? A single core can support multiple hardware threads. Okay. Now you can write a program that can be embarrassingly parallel, meaning that you can launch maybe thousands of threads, software threads. But if your underlying hardware has, let's say, let's a 4-core processor with SMT enabled, which is 2, for example, so it will be 4 times 2, 8. So at any given moment, 8 of these 1000 can be running. Okay. So did I answer your question, Karthikeya? Okay, yeah, thank you. And good that you put a question. So feel free to post your questions on the chat box, right? Of course, we will have a quick Q&A at the end of the first hour, but I would still welcome you to put your questions here, right? So let's now let me show you a quick demo of what this threading can do. Okay, let me switch to my other screen. 1 second. Okay, let me. So Praveen, I hope we are pretty much on time, right?
No hurry, we are on time.
Okay. Okay, so let me pull up two terminals here. Okay, so the one on the left side is my Office PC, right? Let me quickly walk through the configuration. So here, if you see, it is x86 ISA, and it supports both 32-bit, 64-bit, and it is little Indian ordering of the memory bytes, right? And it has 12 CPUs, right? Here, CPUs and cores are kind of synonymous for us. And the key point here to note is actually there are 6 physical cores, each supporting 2 threads. That's how we get 12 logical CPUs or cores, okay, labeled as 0 through 11. Right, and now coming to the right side. So this is a server, in-house server we have in the department, right? So here, if you notice, again, this is an x86 ISA processor with supporting both 32, 64, and little endian. This is all common, but if you notice, here we have 96 CPUs or 96 cores, right? And another key difference is that here we have 2 sockets, each hosting 1 core. I'm sorry. 1 chip, processor chip with 24 cores in it. So overall, we have 48 physical cores supporting 2 threads, means that we have 96 logical cores. Okay. Now, let me demonstrate how this can be exploited by a simple program, right? So let me pick one small demo example here. Okay, before that, let me show you the. So this is a small Java program, right? Basically, we are taking. Let me scroll down. So we are taking these few parameters as input, starting with the number of threads, right? Okay, let me. So in line number 114, this is the parameter for number of threads, then number of rows and columns of first matrix, number of rows and columns of the second matrix, and the last is choice. Now, choice here is that if there are only 2 choices that can be given, right? So if we, sorry. So if we give choice as 1, right, it's going to run the parallel version of matrix multiplication, where we use the thread IDs. And if we give anything else, let's say 0, it is going to run the sequential version, meaning that there is only 1 thread in this, right? So we are not exploiting anything underneath. Okay, let's try to see how the performance is. I hope everyone is clear on the task of the program. We are just multiplying 2 matrices. Okay. Okay. So the first one was the number of threads. Let's say we are running it on 1 thread only, and the matrix size, let's say, is A matrix A is 1000 cross 1000, matrix B is 1000 cross 1000, and the choice, let's say, is 1. So we are just reading how many logical cores are there. right? And here, okay, the time is shown, the number which is shown is actually time in milliseconds, 3010 milliseconds. Okay, so we took this much time, and now if we try to run the other version, right? So we have, because we said only one thread, right? The serial version is doing much better. Okay, now let's increase the number of threads. So because we have 12 threads, let's start with simple, let's say 2 threads and the parallel version. So from
No,
yes,
Kalyan, please check the arguments one more time. I think
okay,
one is for serial version and other than one is a parallel version, right?
okay. If I miss it, let me quickly check. I'll open it in the other window. Okay. Yeah, one is the serial. Sorry for that. Yeah. Yeah. So one is the serial version, and 2 is the anything other than 1 is the parallel, right? So let's try to parallelly. Or maybe I can simply give 0 here. So if you notice here, if we make available 2 threads, and underneath, if we still want to run it sequentially, right? It was taking 2599 microseconds or milliseconds. But if when the moment we said we can run it parallelly, the latency dropped to 1362 milliseconds. Right now, if I further, let's say, increase the number of threads, let's say to 4. So the execution time now dropped to 704 milliseconds. So you are actually seeing a speed up in the performance. And we are still running the same matrix multiplication of 2000 cross 1000 matrices, right? So let's increase it further and see what's happening. So here we see an increase in the time from 704 to 870. Okay. Now let me quickly increase it further and show you. So if we increase the number of threads, again, it has increased to 979. So if I give all the 12 threads, right? Basically, we are tapering off somewhere at 800 or 700 milliseconds, right? This is primarily because the memory overhead or the synchronization overhead is dominating the compute overhead. Till the point where we were able to run it on 4 threads, right? We were able to get the best timing. And now beyond that, if we keep increasing the number of threads, the threads keep waiting longer, basically for data and sync up than the actual compute. Now let me run the same thing on the server, right? On the right side terminal. Okay. So let me start with one thread again. 1000 cross 1000 for A, 1000 cross 1000 for B, and the sequential version. So we have 96 cores on this, and the sequential version is taking 1782 milliseconds. Right now, let's try to use 2 threads and just enable the thread aware, right? So the execution time dropped to 996, and we can continue it further. Again, we will see that the performance will taper off after some time. So if I engage 4 cores, so it is dropping to 5 and 7. Then 6 or maybe 8. Let's try that. So it has come to 302. Let's try to engage 12, 239. And if I, let's say, engage 16 threads, so it is 231. You see that it is tapering off, right? If I engage 24, then it started increasing again. Now the communication overhead and synchronization issues are more, right? And let's increase to 32. So yeah, so we and practically again run it on 96 cores that are available, the same. So it is now somewhere in the ballpark of 300 to 400. So even though we see that it has it was tapering off right from 16 cores itself. Now, if I increase the problem size, let's say increase the size of matrix like this, 2000 cross 2000, right? Now let's see if there is any benefit. Okay, there are some queries here. Okay. Okay, let me complete this first. Okay, on 12 cores, this 2000 cross 2000 matrix is now taking 4,333 milliseconds. Right now, let's try to increase it to 16. We see a benefit here because the compute overhead is still higher. Now let's increase it to 24. VCR, we are seeing still benefit, right? Let's try to increase it to 32. Yeah, now we see that it is tapering off, right? So either it might be because of the synchronization issues or the memory bottleneck itself, because even though we have multiple threads potentially running, maybe the data of those threads is not readily available to us in the caches. That is the fastest memory that we have other than the registers. So, but one quick takeaway here is if there is parallelism available in the program, you should indicate that so that whatever the parallelism available in the hardware can be exploited, right? This is this fund is primarily to emphasize on the point that we should start thinking parallelly, right? Again, repeating the same thing, that we are still doing the same task of matrix multiplication, and matrix multiplication is one of the most heavily used operations. Okay, even in the many of the machine learning and AI or image processing applications, etc. Right now, let me answer the queries. Can all cores on the server be addressed as a single address space? So, Milan, address space is more pertain to the programs, right? Not the physical cores. Or maybe I misinterpreted your question. Can you please rephrase? In the meantime, let me try to answer Vivek's question. Okay, you have just joined now. So we are recording it, so hopefully you can go through it at later point of time, right? Divyanshu has a question that can you run 4 threads in a sequential mode? Yes, we can, but basically each thread will be waiting for the other to complete, right? So let me do that. So let's take 16 and make it sequential. Okay, let's, for comparison, let's quickly run it on parallel. So this is 3354 and let's make it sequential. So you clearly see that it's taking quite a bit of time. Okay, Milan has. Okay, can a single program be transparent to the slots and core? Should be different from cores from the same slot. Acha, you're talking about the multi-threading part. Each thread has an instance, right? And if both threads are practically working on the same problem, right, on the same program, then the address space will be same, right? Otherwise, we cannot execute on in parallel. I hope I answered your question. Okay, thanks, Milan. Okay, Shavik, can you re-explain the difference between threads and cores, and also difference between parallelism and sequential? Okay. Okay, so let's address the sequential and parallelism part. So if you take the simple matrix multiplication program that we're currently looking at, right? If it is 1000 cross 1000, basically you have to calculate 1000 cross 1000 elements of the product matrix also, right? Now in sequential mode, you will be calculating each element one at a time, right? Meaning that 10 power 6 elements will be calculated one after another. Now, just for discussion purpose, if we say that one element is taking 1 nanosecond, right, then the sequential version can potentially take 10 power 6 times 1 nanosecond amount of time. Now, what is the parallel version of it is we can, because the calculation of one element and the other element are practically, independent. So we can, based on the number of threads, hardware threads that are available in the hardware that you are running, right? Let's say if there are potentially, let's say 16 cores, you have a 16 core processor, then you divide this matrix logically into 16 groups of 16, right? And run one element, give the task of one element to each core. Anyways, Dr. Praveen is going to explain further on this, right? So there we are actually calculating 16 elements of the matrix in parallel, right? Now again, if we extend the same analogy that we saw earlier, that if one element is taking 1 nanosecond, because the 16 are being calculated in parallel, now we are able to get 16 elements in 1 nanosecond, right? Now the 10 power 6 elements of the product matrix, how much time it will take is 10 power 6 upon 16 nanoseconds. So it's like 16 times faster. Is that clear, Shovik? And okay, can you re-explain the difference between threads and cores? Okay, let me repeat the same thing that I said a while back. We have software threads and hardware threads. So what I was explaining in the slides were the hardware threads or hardware contexts, you can say, right? So from the hardware point of view, what we are doing is we are using the same execution units, let's say the adder, subtractor, multiplier, divisor, or comparator, etc., right, for two different sets of instructions. Then it would be when we can say that there are two hardware contexts that can run on the core simultaneously. Now, when we talk about the software, Dr. Praveen is going to explain a while later that we can practically divide it into the program into a number of threads based on the task that is at hand, right? So those are the software threads. Hardware threads are limited in number. Software threads are practically infinite based on the task that you're doing. Now, what we do at the runtime is map these software threads to the hardware threads and run them based on the availability of the hardware. Is that clear? So just to extend the same reasoning here. When we are trying to run the program sequentially, right? We are not actually using anything in the hardware. We are just using probably hardware of one thread only, right? But when we are saying that the program can be parallelized into 2 threads or 4 threads, right? Now, if your hardware has still only 2 threads, 2 hardware threads, these 4 software threads will work whenever will get mapped to these hardware threads based on the scheduling that the OS will do, right? And whenever there is a long latency event, then another thread will be picked and it will be executed. Another software thread will be picked and executed. Okay. So any other questions?
If no more
Okay.
questions, we can take a break, right?
Yes. Okay, let me stop my screen. How do I stop here? Yes. Okay, so Dr. Praveen, shall we all
Yeah, we can give a
go or
break
we can
around 10 to 11 minutes. We can start the next
okay.
session at 7:15.
Okay, so are we going to close this session now and
Yeah,
restart again or what?
yeah,
Yeah, I
no
think that
problem.
would be better,
Just
I guess, right?
yes, that is anyhow. I would like to pause the session.
Okay.
Okay, that's it. If they have any problems, we can address those queries during this break time.
Okay. Okay.
Okay, okay. Thank you. Thanks to one and all. Again, we'll catch up at 7:15.
Yes, sorry that I ate up 5 minutes of your current session, but yes,
No,
let's stick to the time and let's meet at 7:15.
yes.
Seconds. Will there are programs be able to execute during those? So, do you mean by programs as in different processes running on system? If yes, then yes, nothing stops us from running multiple processes in parallel. For example, operating system is anyway running on the system when we are running multi-threaded program. There will be preemption of threads, maybe OS and applications, or even like other applications with your applications. So in ideal scenario, if you are looking for a speed up number, you should not be running a heavy loaded processes in parallel with the one which you are running. For example, in this case of 96 vCPUs. So OS doesn't stop running multiple processes in parallel. Does that answer your question? Yeah, good. So the second question is how much is the impact of languages, Python versus C? Yeah, the one liner is there is a huge impact of languages on the performance. The reason being C is a very low level language that the constructs from C directly translates to, not directly, but more or less translate to the assembly, or you can force it to translate. But Python has like high level language. There are high level wrappers around it. So basically, Python will have at the backend CPP code, and it is the interpreter. So the compiler doesn't do a great job in creating a good binaries for that. So yes, language has a huge impact on the performance as well. I don't have C background, but
So was the question from AS answered, addressed?
Not yet. That is what I was going through and trying to think what should we suggest.
See, if you are looking to just parallelize the task that you have and run it on multiple cores or maybe on the GPU, then you need not actually look at the finer details of the pipelining and execution stages, etc. That is not required. Okay, you can abstract yourself at thread level. Basically, what it means is assume that you have multiple threads in the hardware, right? And focus on how you can effectively parallelize your program. I hope I was able to answer. Okay. Yeah. So, Praveen, Saurabh, if you want to add, you can please. Thanks.
Yes, Dr. Kalyan discussed about a simple matrix multiplication by using multiple threads, right? At the same time, he also discussed about execution time, right? Okay. When we look at the execution time of any program, suppose execution time depends upon many factors. Okay, when we are talking about high performance computing, okay, the main purpose of this HPC is we have to reduce the execution time by making use of available resources. Okay, so in this session, I would like to discuss about what are the factors that affect the execution time. Okay, when you look at this particular factors, usually execution time depends upon four things. One is a type of the operation, second one is a type of operands, third one is location of operands, and fourth one is type of the circuit. Okay, type of when we look at the type of the circuit is not in our hands. Okay, it depends depends on the manufacturer. Suppose if you use the AMD chips, they will use one circuit. If you use Intel chips, they will use some other circuit. If you use Apple chips, they will use some other circuit, right? So type of the circuit is not in our hands. Okay, so to reduce the execution time, what can be done? Okay, so to reduce the execution time, we can consider location of the operands, because location of the operands impact the execution time, right? For that, I would like to explain that particular one by considering very simple example. That example is by using a simple operations on a particular array. For that, we developed a simple program. Okay, that one is cache operations. Okay, are you able to see the screen? Are you able to see my screen?
Yes, Dr.
Yes, sir.
Okay. Yes. For that, we developed a very simple program. With the help of this particular simple program, I would like to discuss about how the execution time depends upon locality of operands. Okay. What is the meaning of the word locality? Suppose whenever we look at our simple configuration of our system, here you can see that my system configuration is this one, right? It is the number of cores is 8. That means number of logical cores is 8. That those 8 logical cores spread across 4 physical cores. Each physical core supports the concept of hyperthreading. That means each physical core acts as a 2 logical cores, right? That's it. Okay. Along with that, okay, so to write multi-thread codes or multi-thread programs, one should have some idea about architecture. Okay. In that architecture, actually, we should have some idea about memory. At the same time, how the cache memory is distributed, how many types of cache memory is there. Okay, we should have some information. When we look at my laptop, you can see that I have the 3 levels of caches. To know about levels of caches, there is simple command in Linux, get conf -a grep cache. Yeah, here you can see that there are 3 levels of caches: L1 cache, L2 cache, and L3 caches. Size of the L1 cache is 64K, and size of L1 D cache is 32K, and L2 cache is this is 512K, and the size of L3 cache is 4 MB. Okay. Oh, yes. Suppose if data is in L1 cache, we can quickly access the data. That means to access the data from L1 cache, it takes 1 or 2 clock cycles. If data is not available in L1 cache, then request goes to the L2 cache. If data is available in L2 cache, then we can access it within 5 clock cycles. If data is not available in L1 or L2, then request goes to the L3. If data is there in the L3 cache, then we can access that particular data in, let us say, 20 clock cycles. If data is not available in any one of these 3 caches, then request goes to the main memory. Okay. So if our program is cache friendly, then we can quickly access the data. Okay. Then we can reduce the execution time. In that context, okay, I would like to show the execution of a simple program. Based on that, you may know the importance of cache friendliness while writing multi-thread programs or multi-thread codes. Okay. Yes, for that, we developed a very simple program, that is mycacheoperations.java. Okay. When we look at this particular simple program, here what can you see? Here we considered 3 arrays, A, B, and C. We initialize A and B. We initialize A and B with some values. A is initialized with I, and B is initialized with some random number, right? Okay. So in that context, from this particular function as assign values, here you can see that A of 0 is initialized with 0, A of 1 is with 1, and so on. A of I is initialized with I. Okay. And B of I is initialized with some random number in the range 0 to num. Okay. Right. From this particular example, here, what can you see is that here I consider 2 functions. One is read random. Second one is read sequential. Okay. When we look at this particular function, here what can you see? Here you can see that C of I equal to A of B of I. Based on this particular initialization, how are we going to access the elements of A? We are accessing the elements of A in random order. That is why that function name is read random. Okay. if you look at this, some other read sequential function, here we are accessing the elements of B in sequential order. Here we are accessing the elements of B in sequential order. That is why this particular function name is read sequential. Read sequential. Okay. I would like to give. I'm going to give a simple demonstration on this particular program. Okay. Let us see. Here in this particular program, what I'm going to do is, okay, here I'm going to consider a simple, I'm going to consider two arguments. Here, first argument is size of the array, and the second argument is choice. Okay, choice. If choice equal to 1, okay, I'm going to perform read sequential. That means we are going to perform a sequential access on a particular array, or we are going to call read sequential method. If our choice is other than 1, we are performing a read random. We are performing read random. Here, what are we going to do is, with the help of these two lines, okay, we are going to measure that particular execution time of that particular function. If it is a read sequential, we are measuring the execution time. Suppose other than read sequential, if we call the read random, then we are measuring the execution time. Okay. Now I'm going to execute this particular one. To execute this particular one, how do we execute Java code? You have some idea on that. Okay. To execute that particular one, Java C, mycache operations.java. It is successfully compiled. There are no errors. Java mycache operations. Okay. First, here we are going to pass two arguments, right? First argument is size of the array. If the size of the array is at 10 power 7 elements, okay, that is 10 million. And first parameter, the second parameter is 1. If second parameter is 1, then that is a read sequential. Suppose if you're going to access 10 power 7 elements in sequential order, then it is going to take 26 milliseconds. Then it is going to take 26 milliseconds. Instead of that, if we access 10 power 7 elements in a parallel order in random order, then it is going to take 161 milliseconds. Okay. Here you find the great difference, right? So if we use the sequential access, then it is taking 26 milliseconds. If we access the elements of the array in random order, then it is taking 161 milliseconds. So from this particular example, takeaway point is, okay, execution time depends upon location of operands. Location of operands. That means if operands are available in the cache, or if the data is available in the cache memory, we can quickly access the data. If data is not available in the cache memory, then request goes to the main memory. To access the data from the main memory, we have to spend some amount of time. So while writing multi-threaded codes or HPC codes, we have to see that, okay, our cache, we have to see that required data should be available as close as to the processor. Okay. If the requested data is available in either in L1 or L2 cache, we can quickly access the data. If data is not available in L1 or L2, then it is going to take more amount of time. Okay. Yes. One more reason is behind that. When we write a single thread code, there is no problem at all. Usually, performance difference is very less. When we are working with multiple threads, that means suppose if you write a program with 100 threads, if you are going to execute a particular program with 50 threads, okay? For all these 50 threads, if data is available in L1 or L2 cache are very close to the processor, we can reduce the execution time a lot. Okay, that is the takeaway point from this particular example. Do you have any specific questions on this? Please unmute yourself and you can ask the question, right? Yes, when you look at what is that? Here, yes, Abhi. Sir, can you explain why sequential? Why is sequential closer to cache and random is not? Okay, good question. Here, question is why sequential method takes less time as compared with read random? Okay, that is the question, right? Okay. Here, point is when we look at this particular example, if this is an array, this is an array of 10 power 7 elements. 10 power 7 elements. Suppose initially the processor puts a request for this first element. Okay. Assume that that first element is not available in the cache. In that context, a block of data is transferred from main memory to the cache memory. In that context, along with this particular one, this element, we are going to transfer, assume that we are working with integers. Each integer variable occupies 4 bytes of memory space. In that context, we can actually, if requested data is not available in the cache memory, a block means size of the block. Here you can see that size of the cache line is 64 bytes. So within the 64 bytes, we can keep 16 integers. 16 integers. That means whenever we put a request for this particular integer, along with that particular integer, all remaining 15 integers are transferred from main memory to the cache memory. Okay. In a sequential access, in the next time, whenever we put a request for the next element, okay, we can observe a hit in the cache. Okay. In that way, okay, what will happen is for a particular block, first time we observe a miss. For the next 15 times, we can get a hit in the cache. So in that context, okay, execution time is less when we call the read sequential method. Suppose whenever we call a read random, in that context, what will happen is first time we are going to access A of 0. Okay. Next time, in that context, a processor transfers a block of data. That means A of 0 to A of 15. All those 16 elements are transferred from main memory to the cache memory. Next time, whenever a processor puts a request for A of 100, because read random, it can be any number in between 0 to 10 power 7 minus 1, right? In that context, next time, whenever processor puts a request for A of 100, A of 100 need not be available in the cache. In that context, again, request goes to the main memory. Again, it transfers a block of data. In the next cycle, processor puts a request for A of 1 lakh. In that context, again, there is a miss in the cache, right? That is why we can find more number of cache misses when we call that particular read random method. Did you get my point? Did you get my point?
Yes, sir.
Okay. Next one is Dr. Kalyan discussed about this particular one, right? Matrix multiplication, right? Okay. Matrix multiplication, actually, one of you raised a doubt that execution time is dependent on whether the execution time depend on the language. Yes, execution time depend on the language, right? Suppose consider here I'm going to execute the same program on Java, right? Java C, my matrix operations. No problem. After that, I'm going to execute it by my matrix operations. First one is the number of threads, 1. Second one is order of the first matrix. And fourth and fifth is order of the second matrix. Okay. Next, last argument is either read or seek. Okay. If it is 1, then let us see. Here execution time is 2915. That means 2.9 seconds or 2915 milliseconds. Okay. This program is written in Java. This program is written in Java. Here I would like to explain the same program in C. Here when we look at this particular one, matrix operations.c. When you look at this particular program, this is also just like a simple C program to perform the matrix multiplication. Okay. This is a simple C code. It is not a OpenMP program. I'm going to execute this particular simple C program. Okay. You know how to compile a simple C program, GCC, matrix operations dot C minus O, executable name, matrix operations 1. Okay. Matrix operations 1. Okay. What is the first argument? First argument is I think number of threads. Second one is size of the matrix, right? Yeah, I forgot. I would like to verify that. When you look at these arguments, parameters, what are the parameters we have to pass? We have to pass only one parameter, that is size of the matrix. Assume that both the matrices of order 1000 cross 1000. Both the matrices of order 1000 cross 1000. Okay. 1000. Yeah. Here now we are going to multiply two matrices of order 1000 cross 1000. Here execution time is 7.08 seconds. Okay, here you observe that Java takes less time, right? I observed that your Java C programming is going to take more time. But many optimizations can be performed on this particular C program, right? If you do those optimizations, then we can reduce the execution time. Okay. What are the optimizations that can be performed on this particular C program, right? There are many compiler optimizations. Suppose I'm going to perform simple compiler optimization. GCC hyphen O1 or O0. There is no optimization. If there is no optimization, then execution time is operation 0. Thousand. O0 means there is no optimization at all. Then execution time is 7.24 seconds. This is a simple sequential program. There is no parallel version at all. Okay. We are going to compile the same program with option O1. Okay. When we execute the same program with optimization level 1, then same program can be executed in 4.44 seconds, right? There is a drastic change, right? Okay. Here we haven't changed the code, right? We simply change the flag, right? Instead of actually that too, those are the flags provided by the compilers itself, right? O0 means with no optimization, O1 means with some optimizations, right? Next, instead of O1, if we perform the one more optimization, that is suppose O2 is there, O3 is there, I would like to compile the same code with O3 option. When we compile the same program with O3 option, executable is matrix of 3. Yeah. Same program can be executed in 2.28 seconds. Here, what can you see? Here you can see that this simple C program is much better than that particular Java version, right? Just like that, we can use the different compiler optimizations, okay? While executing a particular program, we can reduce the execution time. This is not a parallel code. This is simple sequential code, but we compile this particular simple sequential code with the different flags, okay? Are you with me? Do you have any doubt? Is there any problem? Are you with me?
Yes, sir. Yes, sir.
Okay.
Sir, what is the secret here, sir? What exactly, what optimization does the compiler does with O0, O1, O3?
Yes. Actually in O0 means there are no optimizations. O3 actually compilers will perform different types of loop optimizations. Okay. Loop optimization is a part of compiler optimization techniques. Whenever it performs loop optimization and loop unrolling, there are many different techniques. If we perform loop unrolling, okay, we can eliminate many jump statements in the low level code. When we eliminate many jumps in the low level code, it is more suitable for pipelining. If a code is more suitable for pipelining, we can reduce the number of stalls and we can get the less execution time. That is the secret behind that.
Okay. Thank you, sir.
Okay. Next one. Next one is
Sir,
actually,
sir,
yes.
yeah. So are these compiler optimization part of the GCC compiler, or did you write a separate
No. I don't.
class for?
Yeah, I haven't written anything. Writing. I'm using the flags which are there in GCC itself. Yeah, that's what. That's what. Suppose before going to write any multi-thread code, first of all, we have to use the all available optimizations provided by the given compiler. On the top of it, we have to write the parallel code. Suppose, consider this particular simple matrix multiplication. We compile the same program with the O3 option. Then execution time is 2.28 seconds, right? Are you with me? Now, I'm going to consider parallel. I'm going to write a parallel code for this simple matrix multiplication logic. When we look at this particular parallel code, how I'm going to write simple parallel code, I'm going to parallelize this particular one using OpenMP. OpenMP is a kind of shared memory programming. Anyhow, actually, Dr. Saurabh will discuss about this particular OpenMP thing. Here, I would like to execute this particular one by using this OpenMP directives. Yes, that's it. Okay, I added few lines of code here. Okay, when I add few lines of code, I'm going to compile this particular one minus f OpenMP. Okay. Here, what is that error? Yes, here number of threads. Okay. How do you consider this particular one? When we are working on when we are writing multi-thread code, give the number of threads. Yes. Here, when the number of threads is suppose same program and the number of threads is 2, we can get the answer in 1.21 seconds, right? Earlier it is 2.28 seconds. If we execute the same program with 2 threads, we can get the answer in 1.21 seconds. Okay, instead of 2 threads, if you execute the same program with 4 threads, we can get the same answer in 0.94 seconds. Are you with me?
Yes, sir. Thanks a lot. Is there any, as a follow-up question, are there any guidelines for choosing the compiler optimizations? Any cheat sheets?
Usually we are going to compile for HPC applications. We are going to compile a particular program with O3 optimization. Usually we follow O3 or OFAST. Okay. Again, it depends upon actually when we look at the documentation of that particular GCC different compiler optimization. Suppose, are we going to optimize the low-level code, or are we going to are we looking for uh, reduce the execution time? Are we looking for reducing the space? Okay, if you want to reduce the space, then we have to compile with different optimization. Okay. But suppose if if we are looking for time, then we had to compile the same program with one flag, different optimization flag. Okay, just explore it. You can have the different flags are there: O0, O1, O2, O3, O fast. Just like that, different flags are there. Just write a simple C program and compile with the different flags. Okay, generate the executables and give the parameters for those executables. You can check the run times.
Perfect, sir. Thanks a lot.
Yeah, that is the thing. So from this particular example, what can you see that? Well, you can say that execution time depends upon kind of language are we using. Okay. For a simple sequential version, if you use the Java, then it's going to take some amount of time. If you use the a C program, it is going to take some other amount of time, right? Suppose if you know how to write that simple matrix multiplication program in assembly language, okay, then you can reduce the execution time a lot. But writing the program in assembly language is somewhat difficult as compared with writing the program in C or Java or Python. Okay. Next
Yes, sir.
one.
Thank you.
Okay. Next
So,
one
sir,
is yes. Please go ahead.
sir, what was the flag for GCC that was if OpenMP that was?
OpenMP, right?
What does that do?
Flag minus F OpenMP.
Yes.
F OpenMP minus F. Anyhow, all these things actually think that Saurabh will discuss it. Today,
Okay.
I would like to discuss the basics. That's it. Okay. Anyhow, I think that Saurabh will give more clarity on how to write OpenMP programs right from the scratch. Okay.
Okay.
Right. Next one. Today, I would like to touch one more point. That one is execution time depends upon type of the operation. Okay. Actually, in cache program, actually, I discussed the execution time depends upon location of operands, right? Okay. Now, I would like to show one more program. That program gives intuition on execution time depends upon type of the operation. Okay. Usually, I would like to give a simple example for this. Yeah. If you look at this particular simple program, here, what can you see? This is very, very basic program. Here, I consider two arrays, A and B. Okay. In that, when you look at the constructor, this particular function, I initialized these two arrays with some size. That means let us assume that size of the array A is 10 power 7 and size of the array is 10 power B is also 10 power 7. Okay. Next, after that, I initialized both the arrays A and B with some random values. A and B with some random values. Okay. Yes. On the top of it, here I'm performing a few operations on these with these arrays, right? When you look at these operations, I'm performing first one is add operation. In add operation, I'm going to add A of I and B of I. I'm storing the result in B of I. Okay, that is simple add operation. Okay. Next one is in subtraction operation. I'm going to perform A of I minus B of I and storing the result in B of I. When we look at the multiplication operation, I'm performing A of I times B of I and storing the result in B of I. In division operation, I'm performing E of I over A of I and storing the result in B of I. Okay, these are the four simple operations, nothing great in that. Okay, when we look at the loop runs from 0 to size of the array. 0 to size of the array. Yes, when you look at this particular simple main function, here in the main function, we are passing few parameters. What are those parameters? In first one, we are passing this particular one size of the array. Second parameter is the choice. If choice equal to 1, okay, then we are measuring the time to perform the addition. If choice equal to 2, then we are measuring the time to perform the subtraction. Just like that, when choice equal to other than 3, okay, we are performing the time to perform the division operation. Okay, here our objective is which which operation is going to take more amount of time. Okay, and that is the thing. Okay, here when we look at this particular simple program, Java C, my operations 1.java. This is a very simple C program, a simple Java code. I compiled it. There are no errors here. I'm going to execute this particular one, my operation 1. And initially, first argument is size of the array. Here, size of the array is 10 power 7. And for choice is 1. That means addition. To perform addition, we can perform that addition in, let us say, average of 3 runs. It is close to 23 milliseconds. Next one, time to perform this subtraction. This is also average of 3 runs. It is also closer to 23 or 24 or 20, let us say 25. Okay. Similarly, multiplication. Multiplication is also going to take more or less same. Sorry. Okay. If you consider multiplication is also going to take more or less same time. Actually, 1 or 2 runs, we can consider this particular first one is kind of outlier. In multi-thread code, instead of 1 run, we have to consider average of 4 or 5 runs. Okay. If you find that some one or two outliers are there, we simply neglect that. There is no need to consider those outliers. Okay. Now I would like to perform the division operation. When you say that it's a division operation from this particular example, what can you say that division operation is the costliest operation as compared with remaining 3? Division operation is the costliest operation as compared with the remaining 3. In division operation takes an average of 48 milliseconds. Remaining operations take less than 25 milliseconds or 26 milliseconds, right? So from this particular example, takeaway point is, okay, execution time depends upon type of the operation. If we perform the addition operation, take some amount of time. If you perform the multiplication, then it is taking some amount of time. If you perform the division, then it is going to take some different amount of. So integer division takes more time as compared with the integer addition and subtraction. Okay, that is the point. Are you with me? Is there any problem? Do you have any problem? Are you able to follow the lecture? Hello.
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Yeah. The next one is in the next
Dr.
example.
Praveen, there seems to be a question from one of the participants, Vishal.
Okay. Suppose am I trying to run out of memory bound application, how can we map the data? How can we map data close to core? Okay. Here, this is some different question, right? Suppose am I trying to run out of memory bound? What do you mean by memory bound, Vishal?
So suppose HPC applications like HPL, it is a memory bounded application. So how we can map this application in L1, L2, and L3 so that whenever the post call for the data, it is placed close to the cores.
Okay. Suppose if you want to, usually, who will place the data very close to the cores?
Like how we can place that one?
No. Usually, OS will take care of it, right?
Okay.
Okay. OS will place the data very close to the processor. Okay. To place the data very close to the processor, what can be done? If a processor is busy with some other work, okay, we can write some other thing in that particular thing. Actually, whenever we perform a simple read operation, any update operation, then that particular data is fetched to the cache, right? Did you get my point?
Yes, yes.
Yeah. If that means suppose if processor busy with some operation, suppose if you write some other simple fetch operation, then actually what will happen is that fetch operation fetches the data, next data very close to the processor. When it fetches very close to the processor, ultimately we can reduce the execution time, right?
Okay, okay.
Okay.
Got it, sir.
Okay. Next one is in the next example, I would like to discuss execution time depends upon type of operands. Okay. Yeah, actually, earlier example, I considered A and B are of type integers. Now A and B are of type double. Usually, whenever we look at this particular one, integer occupies 4 bytes of memory space, right? Usually, double occupies 8 bytes of memory space. Are you with me? At the same time, integer arithmetic is entirely different from floating point arithmetic. Okay. This particular double things, it is going to follow IEEE 754 standard. When we are working with integers, usually we are going to consider simple 2's complement representation of the numbers and we perform the operations on that. Okay. Now, for this particular program also, actually, I'm going to perform same set of operations, and that is yeah, addition operation, subtraction operation, multiplication, and division. Java C, my operations 2.java, Java, my operations 2. Here 10 power, this is 10 power 7, when choice is 1. Then here see execution time is, earlier execution time is in terms of 20s, right? Okay, now it is execution time is in terms of 35 and 36, right? C. Okay. Next one is, okay. So here takeaway point from this particular one is, okay, floating point division and that means floating point addition and floating point multiplication. All these operations more or less take same time. Okay. In the previous example, actually previous example takeaway point is integer division takes more time as compared with the remaining operations on integers. Remaining operations on integers. So from this particular, from these examples, okay, we can say that, okay, execution time of a program, okay, depends upon type of operations are we going to perform and type of operands are we going to consider and location of operands and type of the circuit. Are you with me? Execution time of any program, either it is sequential one or parallel one or anything, execution time depends upon all these 4 factors. Okay, is it clear?
Yes, sir.
Okay.
Yes, sir.
Okay. Next one is just a minute. Give a minute. Yeah. Uh, Today I would like to discuss about, okay, how to find amount of parallelism present in a given algorithm. How to find amount of parallelism present in a given algorithm. Okay. To find the amount of parallelism present in a given algorithm, okay, we can use master method. By using master method, we can find the amount of parallelism present in a given algorithm. Okay. Let me share the slides. Are you able to see the slides? No,
No,
right?
sir. No.
No. I think now we are able to see the slides, right?
Yes, sir.
Yeah. Now, I would like to explain how to analyze the amount of parallelism present in any algorithm by using master method. I think you have some idea about master method, right? Usually, master method is used to estimate time complexity of a particular algorithm. Okay. When we look at this particular master method, recurrence relation is of the form P of n equal to A times P of n by B plus F of n. Here, what is the meaning of that? Meaning of that is if there is a problem of size n, okay, to estimate the time complexity of this particular problem, we are going to divide that particular problem into A subproblems, each subproblem of size n by B. Okay. Once we have a solutions to those A subproblems, we can systematically combine those solutions to get a solution to the original problem. That is simple divide and conquer strategy. You have some idea on that, right? Are you with me? Okay.
Yes, sir.
Let us consider. Dr. Kalyan discussed about simple matrix multiplication logic. Okay. Suppose if you consider simple matrix multiplication logic, okay, this simple matrix multiplication is embarrassingly parallel. How do we get this particular C11? To get the C11, we are going to multiply this particular row with this particular column, right? Okay, then we'll get the element C11. Okay, so number of multiplications we need to perform to get Cij is n multiplications. N multiplications. So total number of elements in the resultant matrix is if we consider matrices of order n cross n, total number of elements in the resultant matrix is n square. Number of elements is n square. Therefore, total number of multiplications is n cube. Okay, for each element we have to perform n multiplications. Number of elements in the resultant matrix is n square. So to get the resultant matrix, we have to perform n cube number of multiplications. We have to perform n cube number of multiplications. Suppose if you write a simple sequential method, okay, time complexity of this particular algorithm. What is the time complexity of this particular algorithm? Any guess? If we use a simple sequential method, then time complexity of this algorithm is
N cube.
order of n cube. That is pretty much simple and straightforward, right? Okay. Suppose if we parallelize this particular problem, okay, if we parallelize, that means if we solve this particular problem by using multiple threads or very large number of threads, how much amount of parallelism is present in the given one? Okay, how do we calculate the parallelism? There is simple formula to calculate the parallelism. Okay, parallelism is time taken for single thread execution over time taken for multi-thread execution. Some x. When we consider x number of threads, that time taken for x, when we consider x number of threads. Okay, and this particular ratio gives the speed up. Okay, I would like to give a very simple example. Suppose if single thread execution took 2900 milliseconds, fourth thread execution took 725 milliseconds. Then speed up is 4x speed up. Then speed up is 4x speed up. Okay. We calculate the speed up, okay, by using this simple formula, that is time taken for single thread execution over time taken for multi-thread execution. With the help of that, we can calculate the speed up. Okay. For this particular simple matrix multiplication problem, how do we calculate the speed up and how do we estimate amount of parallelism present in this particular one? Okay. If we consider this particular problem, okay, we can solve that particular problem by using divide and conquer strategy. Okay, in that context, we can divide that particular problem into four subproblems. Suppose if this is a matrix of order n cross n, if this is a matrix of order n cross n, then we are going to divide that particular matrix into four submatrices. Each matrix of order n by 4 cross, each matrix of order n by 2 cross n by 2. each matrix of order n by 2 cross n by 2. So to get the resultant matrix, okay, we have to perform 8 multiplications. This is A11 times B11 and A12 times B21. Later, when we perform this particular addition of this particular product with this particular product, okay, then we will get the C11. Are you with me? Are you with me?
Yes, sir.
Sir.
Yeah. Here, actually, when we look at this particular simple logic, okay, from this particular simple logic, here we divided a given problem into 8 sub-problems, each sub-problem of order n by 2 cross n by 2. Okay. Then what we have, we will get this particular one intermediate result, and this one is another intermediate results. When we perform the addition of these two matrices, we'll get the final product. Okay. That is one addition of order n cross n. One addition of order n cross n. Now I'm going to explain amount of parallelism present in this particular one by considering very simple algorithm. Okay, try to consider this particular algorithm. Here you can see that this particular when you look at this particular algorithm, okay, here it takes four parameters. C is used to store the result, and A and B are the input matrices, and N is the order of the matrix. N is the order of the matrix. Okay. Here, when we look at this simple algorithm, here spawn means we are launching a one particular thread to perform this particular operation. Okay. Here we divide a given problem into 8 sub-problems. No? For each sub-problem, we launch one separate thread. Okay. By using that particular thread, we can solve that particular sub-problem. That is the assumption. Okay. In that particular context, here, when we look at this particular algorithm, here you can find there is sync point. Okay, what do you mean by sync in a multi-thread context? Okay, sync means that is a kind of a barrier when we are working with multiple threads. Okay, fastest thread should wait for the slowest thread. Okay, otherwise what will happen is we end up with wrong results. We end up with wrong results. Why should we end up with wrong results? Actually, after performing those multiplications, here we are performing the addition of those two matrices, right? Okay. Suppose here, if we don't wait for fastest thread, should not wait for the slowest thread. Okay, that fastest thread can perform this particular corresponding addition with stale values, right? When it performs the addition with the stale data, then it end up with wrong results. That is why we need a sync point. Okay, when we look at this particular algorithm, what can you see that? Okay, we can see that these 8 multiplications can be computed in parallel. These 8 multiplications can be computed in parallel. At the same time, we can perform this particular matrix addition operation also in parallel. With that idea, I would like to explain amount of parallelism present in this particular piece of code. Okay. When we look at this particular one, okay, here this is the actual code. Okay. This is the simple first 8 are the multiplications. Here for the addition of C comma T comma N is we can perform that particular matrix addition by using simple divide and conquer strategy. Okay. Now we are going to analyze this particular one. You know that the sequence whenever we write a simple sequential code, time complexity of matrix multiplication is order of n cube. Okay, this is a simple parallel code. To estimate the amount of parallelism present in this particular one, how do we estimate it? Okay, to estimate that particular one, we have to calculate span. Okay, span means maximum time it is going to take to perform that particular matrix multiplication. Okay, in that context, first of all, we are going to calculate here. First, we are calculating span of matrix addition. Latest here, span of matrix addition is order of log n. How do we get this particular log n? By using simple this one, we can say master method. With the help of simple master method, we can say that time complexity of this particular add operation is order of log n. After that, here we are going to calculate span of this particular multiplication. How do you calculate span of matrix multiplications? Span of matrix multiplication is, okay, these 8 operations can be computed in parallel. So time taken to perform these 8 operations is, we are going to consider one of those 8. So m infinity of n equal to m infinity of n by 2 plus a infinity of n. Okay, that is the time to perform the addition. Okay, just this particular addition operation also can be performed in log n time. Okay, in that context, with the help of master method, we can say that we can perform this particular matrix multiplication in order of log square n time, by using very large number of threads. Okay, by using very large number of threads. Okay, anyhow, I will share all these slides with you. Please go through it. So to estimate the amount of parallelism present in this particular matrix multiplication algorithm is work by span. Work is single thread execution. See, when we consider single thread execution, time is theta of n cube. When we consider multi-thread execution, time is theta of log square n. In that context, for large values of a, suppose if n value, order of the matrix is 10 power 3, that is 1000 cross 1000, n value is 10 power 3. In that context, from this particular order of n cube, we'll get time is total number of steps is 10 power 9. From this particular log square n, log 1000 base 2 is 10. 10 square is log square n is 10 square. In that context, total speed up is 10 power 7. In that context, total speed up is 10 power 7. Okay, that means actually with the help of that particular simple algorithm, we can achieve 10 power x speed up. 10 power x speed up. Okay, when can we achieve 10 power x speed up? When we have very large number of threads and all the data is available within the processor registers, then we can achieve 10 power x speed up. Okay, but in practice, that should not be the case. Okay, it is very difficult to store all the data in the processor registers, right? So in that context, actually, we can observe pretty much less than this particular one, 10 power 7, right? Okay, that is why this is the theoretical speed up based on the algorithm. And when we develop a code by using some programming language, then are many things comes into picture, right? Okay, that is constructs we consider in a programming language, and compilers are we going to use, and operating system and architecture. All these things affect the performance of any programming language, performance of any program. So to write a multi-thread code, we should have some idea about architecture, operating system, and programming language. Then only we can write better code. Okay, are you with me? Are you with me?
Yes, sir. Sir,
Okay.
what is the base of log here, sir?
What here usually in computer science, base is considered as a 2. Base is 2. Suppose if they don't mention anything, it is base is 2. Okay, based on that only, usually we can solve the problems. Okay, same problem. Okay, when we look at this same for this matrix multiplication problem, one can develop some other algorithm. Okay, if we consider this particular algorithm here, what is the problem with this particular algorithm? Are you able to identify this problem? There is one problem with this particular algorithm. What is the problem with this algorithm?
It's recursive.
Yeah, it is recursive. Even though it is recursive, in each recursive function call, here we are calling that malloc function, right? Silk alloc or alloc function call, right? Whenever that is, we are requesting the operating system to allocate some amount of memory to the temporary matrix. Okay, then what will happen whenever our program puts a request? Then what will happen? It's going to call appropriate system call. With that system call is responsible to allocate the requested amount of memory. Okay, that is the costliest operation. In practice, these type of algorithms gives very less performance. In practice, these type of algorithms give very less performance. Okay, what may be the alternative to this particular one? Alternative to this particular one is, instead of that, we can consider some other algorithm. Here, this algorithm is also similar to the previous algorithm. Here, we don't use the temporary matrix. Okay, we are performing the simple matrix multiplication without using temporary matrix. Okay, when we estimate the time complexity of this particular one, time complex sequential version, here also time complexity is order of n cube. When we calculate, when we consider a span of this particular one is span of this particular one is order of n cube, order of n. This one is order of n. If we calculate the amount of parallelism present in this particular one is m1 of n over m infinity of n, that is order of n square. For a matrices of order 1000 cross 1000, here speed up is 10 power 6. Here speed up is 10 power 6. But previous algorithm speed up is 10 power 7. Okay, that is the theoretical speed up. Okay, but in practice, this second algorithm gives the better results as compared with the first one. Reason behind that is, okay, in this algorithm, okay, we haven't considered any temporary arrays. There we consider temporary matrices. Each and every time we are putting a request to the operating system has to respond to that particular request and allocate the required amount of memory. That is the costliest operation. So while writing multi-thread programs or multi-thread codes, we should avoid such type of costliest operations. Are you with me?
Yes, sir.
Yeah, that is the main point. Suppose that so while writing any multi-thread program, okay, yes, which operations are the costliest operations? How can we avoid those costliest operations when writing the multi-thread codes? Okay, what may be the alternative to that? That is important thing. So actually, to estimate the amount of parallelism present in any program, okay, any parallel prod, okay, you have some idea about master method. Usually, master method is used to estimate time complexity of any algorithm. By using the same master method, we can estimate amount of parallelism present in a given algorithm. Okay, in a given parallel code or parallel algorithm, right? Okay. That is about analysis of simple parallel algorithms, right? Here, simply I can give an introduction to that particular analysis part. Okay. From next class onwards, I don't want to discuss this particular theory because for the remaining sessions also, you should have some idea about background on analysis. That is why in this class, I discussed about the this theory. In the next sessions, I would like to discuss all the topics by considering very simple examples or simple programs. Okay, by using that particular program, I would like to discuss that particular topic. Okay. Do you have any problem or anything, or do you have any doubts? I'm here to clarify your doubts. Any questions? If no more questions, I would like to close the sessions.
So just one question.
Yes, please go ahead.
Yeah, so like you can in that slide where you use the no temporary matrix, the matrix C will still have to be assigned some memory, right? So like
No.
how are the two basically so
No.
different?
No. Actually, here when we look at this is the first one, right? Here you can see the first one, right? Here, suppose C is used to store the resultant. Result. So A and B, right? For A and B are the source matrices. C is used to store the result. For these three matrices, we can allot the memory ahead of time, right?
Right.
Okay. For in each recursive function call, we are allotting the memory for this particular temporary matrix T to store the intermediate results.
Oh, right. Okay.
That is the costliest operation here. While writing multi-thread programs, we have to avoid such kind of operations. Then you look at the second one. Here in the second one, there is no temporary error. Here we are using the simple one multiply and add, right?
Right.
Yeah, we are storing
Okay, sir.
and that is why here in a previous program there only one sync point is required. Here we need two sync points, right?
Right. The operation is happening in place basically in
Yes,
the
that's
matrix
true.
C.
Yeah, when we look at this particular one, here these four operations are executed in parallel. After that, we are storing that intermediate result in C. Next, we are going to perform these four operations in parallel. We are storing the same, we are adding the particular one to the existing one, which is there in C.
Right.
Yeah. At the same time,
Understood.
at the same time, here you can see one more thing. Here, C21 and C21, C22 and C22, C12 and C12, right? It is in a reverse, completely in reverse order. What may be the reason for that?
Because maybe they're already stored in cache.
Yeah, that's good. That's good. That's true. That is the actually that C21 is already there in the cache, right? If we use the same thing here, we can increase the number of cache hits and reduce the execution time.
Right.
That is the point. Okay.
Okay.
What
Thank
else? Oh, welcome. Good.
So one follow-up question over here, sir.
Yeah.
Since we are not creating temporary variables, then then we are reducing the amount of multi-threading that which we can do, right?
Yeah, we can reduce in the amount of that's true. Amount of parallelism here is less.
Then why can't we create those temporary variables ahead of time? How we have done it for C, A, and B?
Then we have to allocate so much amount of memory, right?
Okay, so there is
Usually execution time depends upon memory footprint. Okay. Suppose if our program consumes a lot of memory, then our program takes more amount of time.
Okay.
Right? Did you get my point? Execution
Yeah.
execution time is inversely proportional to the memory footprint.
So I think problem will be if we are multiplying really huge metrics, then
Yeah.
we will be creating unnecessary temporary variables.
Yes. Just try to implement that particular matrix multiplication by consider for the matrices of order 1000 cross 1000.
Got it, sir.
Yeah, usually for machine learning applications, we are working with matrices of order 10,000 cross 10,000, right? If we consider 10,000 cross 10,000 and with the help of temporary errors, it consumes huge amount of memory, right?
Yes.
Yes.
Got it.
Good. Anything else? Okay. Anyhow, I'm going to share all these slides with you. Okay, please go through it. Okay. From the next class onwards, I would like to discuss all the topics by considering very simple programs. Okay, this is the program. With the help of those programs, I would like to discuss the corresponding theory behind that. Okay, I think that is more useful as compared with theory-based lectures, right? Okay. One more thing is anything else? Any more questions? Okay.
Sir, can you provide the code examples as well?
Yeah, I will share the code examples. Actually, today I shared some set of programs. I showed the execution of some programs, right?
Yeah.
Yeah, definitely I will share all those codes with you.
Okay, thank you.
So what language is this?
Pardon?
What language is this? Example like Spawn and like.
No, actually this is Silk language. Actually, this is developed at MIT. Okay. Yeah, don't worry about this particular one. Actually, anyhow, we wrote a multi-thread codes in C and C Java, right? You can easily understand those codes, right? As compared with this particular Silk one.
Sir, another question like where in this example are you defining the metric multiplication function? Like,
Pardon?
Like in this particular example, like where are you defining the matrix multiplication?
Matrix multiplication, right?
matrix multiplication function, because like you need to add, because in the first line click void multi-a, you're defining what is the what will the function take as the arguments,
Okay.
and then you're calling the functions in this point. So
Okay.
where are you defining the multiply C11,
No,
multiply A11?
that is the base case, right? If n value is less than n by 2 value is less than or equal to n by 2 value is greater than or equal to greater than 2, then this is the case. If n by 2 value is equal to 1, then simple element wise multiplication, right? Did you get my point? Suppose if the matrix of order 2 by 2 cross 2 by 2, then that is simple element wise multiplication, right?
Yes.
If matrices of order 4 by 2, 4 by cross 4 by 4, then we are going to multiply 2 by 2 matrices, right?
Yes.
Yeah, we have to write the base case here. Are you with me? What else? Okay. Thank you. Anyhow, I will share all these programs and slides with you. Please go through it. If you have any doubts, most probably we will address your doubts in the next session. Thank you. Thanks a lot.
Thank you, sir.
Thank you, sir.
Just one quick point with the queries. So you can you're free to post your queries on the Google group, right? So we'll be addressing them as soon as possible, right? Instead of waiting for the next session, you can do that. It will help everybody, in fact.
I think that is a good
Thank you.
suggestion. Okay.
Okay. Thank you.